Okay, lesson 3. In case you're wondering why I'm now walking from behind, it's because I don't trust my remote anymore. I recorded some lessons with the remote, and then it wasn't recording for like 30 minutes. I had to do the whole thing over again. So that's why I'm coming from behind. You don't care, but some of you might be like, why would he suddenly appear? And I don't know how to edit a video. I think that's pretty clear at this point. I'm not editing out me walking in. No, not doing that. Anyway, lesson 3, conditional probability. Okay, we're gonna do this, but I promised you in the last one that we're gonna go back up here, and I'm gonna give you, where was it? See, I would edit this out if I was editing videos, but right here. Independent events. Okay. A and B. I told you I'd give you the formula. It wasn't as complicated as I was thinking it would be. Again, it was just multiplying because we know that compound events depend on each other, so you multiply. And typically is a multiplication statement. So the probability is equal to the probability of event A times the probability of event B. And that's what we did. That's literally how we did all these. It's just more I guess, correct or proper, right? If you see it out like this. Dependent events, we do them the same way, okay? We did those in the video the same way, but the probability was A and B. It was the probability of A times the probability of B given A happened. Oh, happened. So what that means, what this means, is the probability of A times B given that A happened. Remember the example of taking the crayon out of the bag. When I took the crayon out and I didn't put it back, that's a dependent event, because the second event depends on the first one succeeding. I pulled out the red crayon, it's the one I wanted, and I threw it across the room. I needed that to happen. So the second one needs to depend, and it will change based on the event A happening. So that's the more formal write-up of it, but pragmatically, how we solve these problems is exactly the same. We did that, I just didn't give it form like this. Okay, but back to here. All right, a conditional probability statement. Given events A and B, conditional probability is the probability of an event B occurring knowing that A has already happened and we have some notation for it. We won't really use it very much, but it reads as the probability of B given A. That straight line means given. So the probability of B given A. Okay. And we have a formula. I'll write it. No, I'm not going to write it. I won't even write it because we're never going to use it. It's silly. We're not going to use it. We don't need to use the formula, just like we didn't need it before. We're just going to think about these problems and we're going to figure them out. Mitchell or no? Gabe drew a card from a standard deck of playing cards. What's the probability that he drew a queen? Oh, it was Mitchell. See, it wasn't Michelle that he drew a queen, given that the card was red. Okay. Reread what is important. What is the probability he drew a queen given that the card was red? Okay. So when we do these problems, your given will always become your denominator. And then the numerator is what we want or the favorable outcome, however you want to describe it. I'll say what we want. So in this problem, the bottom says given it was red. Well, how many red cards are in a deck? Half of them, 26. Again, that paper's right there, but really you should know this. Now, given that it's red, how many queens are red? You have the queen of hearts and you have the queen of diamonds. That's 2. 2 of the red cards are queens. So we reduce, because we always reduce, always. And that is our answer, right here. And we didn't need a formula. We didn't need to make it more complicated than that. The given, the sample space, is the denominator. And of these given, how many are what we want on the top? A number 1 through 100 is randomly picked. What is the probability that it's a perfect square given that it is odd? Okay. Given that it is odd, between 1 and 100, how many numbers are odd? 50. And then how many of those odd numbers are perfect squares? Oh my goodness, okay. We need to figure that out. Perfect squares, 1 times 1, 1. 2 times 2, 4. 3 times 3, 9. 4 times 4, 16. 5 times 5, 25. Okay, you can see how we're building these. Perfect squares follow from here. 36, 49, 64, 81, 100. Am I missing any? 6, 7, 8, 9, 10. No. So these are all of my perfect squares. How many are odd? 1, 2, 3, 4, 5. 5 of those perfect squares are odd. So we reduce 1 out of 10. Okay. So the denominator, given that it was odd, there were 50 odd numbers. Of these 50, only 5 of them fit our category of being perfect square. 62 people take yoga, and there are 62 people that take yoga class and 48 that take spinning class. Okay. 15 people that take yoga also take spinning. If a person from these groups is picked at random, find the probability that they take yoga class if you know that they take a spinning class. So let's build a Venn diagram. This is typically the easiest way to go about these types of problems where we have different groups of people. Let's just build a Venn diagram. 62 people take yoga, so I'm going to call this yoga people. And 48 people spin. 15 people that take yoga also spin. So I have 15 people inside this overlap. They do both. 15 people do both. All right. Now I need to figure out how many other people go in this yoga. Well, 62 people total take yoga, right? So in this circle, I should have represented 62 people. I already have 15 of them accounted for. 47 over there. I still have 62 in my yoga circle, but only 47 of them only do yogis. Now, I'm going to do the same thing over here. 48 people spin, so I should have 48 people represented here, but 15 of them are already accounted for. 33. Okay, so that's our Venn diagram. Now to the question. If a person from these groups is picked at random, find the probability that they take yoga if you know that they spin. How many people spin? How many people spin? 48. Of these 48 that spin, how many take yoga? 15. And then reduce 5 over 16. Building Venn diagrams is the easiest way to tackle these problems. 30 students in Smith's math class, 13 are athletes, 9 are in band. Okay, so we're gonna build another Venn diagram. We have athletes and we have band kids. 30 total kids. 13 are athletes, 9 are in band. If 3 of the athletes are also in band, only 3 in my overlap. All right, that's enough information to fill in the rest of this. 13 are athletes. In this, I should have 13 athletes total. 3 of them are already here, so that leaves 10. 9 band kids. 9 band kids, 3 of them already accounted for, 6. Okay. If one student is chosen at random, find the probability that this student is in band if we know that they're not an athlete. Okay, so quick pause. There are 30 kids in this class. The most astute of you may notice that there are not 30 kids represented in my Venn diagram. Okay, so 30 kids, and I want, it is known that they are not an athlete. They are not athletes. Well, how many kids total are athletes? 13. If I want a kid that's not an athlete, 30 kids take away the 13 athletes gives you 17 kids to pull from. That's going to be my given. 17 kids, okay, not athletes. Now, what does it actually want? Find the probability that the student is in band if they're not an athlete. So I don't want any athletes, none. Only 6 kids are in band that are not athletes. That one can be tricky. Okay, that one can be tricky because the other one, the other example we just did, everyone was represented in this. The yoga people and the spinning people. Everyone was there. Not everyone was represented in this problem. There are kids who aren't athletes or aren't in band. Okay, so pay attention to the problem. Okay, really read it. Give it some thought. This is a unit about really taking the question and like mulling it over and figuring out what is the important information. A lot of critical thinking in this unit. Okay, so now we're talking about two-way tables. A two-way table is just a different way to organize different groups of data and represent them visually. The table shows the results of a poll of 50 kids randomly asked if they prefer to watch hockey or football. Find each probability. Okay. A says the probability who like football given that they are a girl. That line means given. Given that they are a girl. So remember, given's our denominator. Given will always be our denominator. How many girls do we have total in this table? 6 and 16 make 22. Okay. Of these girls, how many prefer football? 6. Okay. Probability of boy, given they like hockey. Okay, so hockey is going to be my denominator. In this table, how many total hockey lovers do I have? 10, 16, 26. Of these 26, which ones are the boys? 10. Okay, all right. Maybe I'll try representing this a different way in the next problem, but that's foundationally how this works. Okay, we got a more complicated table. Just a little bit more complicated, but not really. The table shows the results of 150 randomly selected middle school students who are asked if they take French or Spanish. Okay. I want to find the probability of a 7th grader who takes French. So, I need to turn the page. I'm pulling there's no given here. Here's a given, here's a given, here's a given. Given is always my denominator. There's no given here. So this is saying I'm just finding the probability of a random 7th grader who takes French. So I can pull from anyone. There's no denominator. 150 total possibilities. Okay. Of everyone represented, how many fit the category of 7th grade who take French? 7th grade, French, 25. So when you don't have a given, use your entire sample space as your denominator. Probability of 8th grade, given that they take Spanish. Okay, so here's maybe a different way to write this. Given that they take Spanish. Here's all my Spanish kids, all of them. And given is my denominator. So how many total are represented here? 68. Yeah, 68. Of these Spanish people, I want 8th grade. I want 8th grades. 8th grade. Looks like 33 fit my category. And I don't believe that reduces at all. Okay, just checking. Notes, does it reduce? No, good. Okay. Okay, we can follow the same type of pattern if the highlighting is working for you. Probability that they take French, given that they are a 6th grader. Given 6th grade, how many 6th grades do we have? Given as my denominator, I have 42 6th graders represented here. Now, how many take French? Where are my French kids? So 6th grade that take French, that's where my double overlap is, 19, and also that does not reduce. Okay, you can always build them like this. Last one. They take French. So how many total French kids do we have? 44 plus that is 82. Okay. Of these, how many are 7th grade? Some of you already know what it is, I hope. 7th graders, we're already 7th grade. Boom! My overlap is 25. And this is a lot of answers that do not reduce. But that's how these are done. Okay. So whether or not you need the visual of the highlighting, or can just look at it and simply figure it out, both roads, not that hard. The table shows results of a poll, randomly selected juniors and seniors who were asked if they're going to prom. Okay, so letter A here, number 1, does not have a given. It doesn't have a given. So my bottom is going to be my entire sample space. How many total people are represented here? I don't want to add that in my head. I just don't. It's early, okay? It's Tuesday and it is 10:30. I don't want to add that. So it looks like it's 200. That's convenient. There are 200 total people in this survey. Now I want to find a junior that did not attend prom. I want a junior who said no, 56. Okay, reduce that if you can. It's going to be 14 over 50, which goes further to 7 over 25. All right, did not attend prom given that they are a senior. Seniors, senior, senior, senior. How many total seniors are here? 116. Of these seniors, how many did not attend prom? 19. Probability that they're a junior, given that they said yes to prom. They said yes to the dress, which is a reference that only the old people will probably understand in the room. So given that they attended prom, how many kiddos attended prom? Yes, they went to prom. Looks like 125 kids attended prom. Of these, how many are juniors? 28. And that will not reduce. Okay. Two-way tables are a really good way to represent and get probabilities. They're simple to read and use. Okay. Frequency tables, however, are a little bit more involved. The table shows the number of first class and coach class passengers on a plane who checked 1 bag, 2 bags, or didn't have any bags at all. Maybe they were fleeing from the country. Who knows? Okay, sometimes you just gotta get on a plane and you don't have time to pack your go bag. Find the joint relative and marginal frequencies, then find each probability. Okay. So how we're gonna do this, first we need to figure out how many total people were on this plane. I'm gonna add together everything here to figure out how many people, and that's 20, 80, okay, so I got 80 here, and then I got 28, another 80, so 160 people. I got 160 total peeps who are flying on this plane. Okay. Now this box here, first class and 2 bags, that box will correlate and match first class 2 bags over here. How this is different is we're just finding the percentage. We're taking the number here, this representative of the total population, we're turning it into a percent. So 16 people were in this category. 16 of the 160 total that are on the plane. That works out to be 1/10. And our calculator will tell us that 1/10 is worth 10%. 10% written as a decimal is 0.10. That is how we build this. Okay. And I'm gonna grab a calculator real quick because not all the other ones are so nice as that one was. This bag of first class and 1 bag, those boxes correlate. 12 out of the 160 belong there. 12 divide 160. It's gonna be 30/40, but that fraction doesn't really work nice for me. So if I convert that to a decimal, my calculator will do that. 0.075. Okay. And no bags 2. Out of 160, and that's going to be 1/80. .0125. Okay, so that's how we build each of these boxes. 0 bags first class, 0 bags first class. They match. The total. We're going to add these decimals, and we're going to fill in this amount right here. I have 0.10 plus 0.075 plus 0.0125 for a grand total of 0.1875. We're gonna redo the same thing for every other table. That's how we build them, but I'm just gonna write the numbers because the process is right here. So, coach class was represented by 0.325. Next one, 0.375, 0.1125, and then that gave us a grand total of 0.8125. Okay, let's take a minute to first off copy those if we didn't figure out them already. But let's take a look at what this represents, okay? So a lot more people fell in this category here, coach class with 2 bags, than did here. This number is a lot bigger than that one, so that makes sense. The vast majority of people afford coach. That's not shocking. Not a lot of people can afford first class. So when we totaled the amount of people, a lot more of the population is represented here than it is here. 0.81 is huge compared to 0.18. A lot more people were here than here. So this makes sense. So now to get the other total column, we are simply adding, and I can do the first one, 2 bags. How many total people had 2 bags? This plus that, 0.425. And then we're gonna add to the right, 0.45. And then the last one to the right, 0.125. to get this final box, you can either add down or you could add right. Either way, it should always equal 1. Why is it always 1? Why is that box always 1? Because this represents both totals. That represents everyone on the plane. And 1 as a percent is 100%. It's everyone. Everyone's included right here. Okay. So building the table takes a little bit of time, but it helps us get these answers quickly. Find the probability that a coach class passenger that did not check any bags. So I need to find coach class who had no bags. This number right here, 0.1125. Now that's my answer, but keeping it as a decimal is kind of gross. Probability, we always talk about percents, or maybe a fraction. Like, what is the probability it's gonna rain tomorrow? I don't know, 42%, okay? You wouldn't say, what's the probability it's gonna rain tomorrow? 0.42. No, we don't talk about it like that. So, to change a decimal to a percent, you take that decimal and you move it 2 to the right and you plop it down. This is the same thing as 11.25%. Probability of first class passenger that checked at least 1 bag. So I want first class, I'm living in the first class column, and at least 1 bag. That's gonna be 1 bag, but also 2 bags, because that's at least 1, right? Add these two together, you get 0.175. And if I'm gonna convert that to a percent, I'm gonna take this and drag it 2 to the right, 17.5%. Coach class, given that they checked 1 bag. How many people checked 1 bag? How many total people on the plane checked 1 bag? 0.45. Okay. Now, of these people who checked 1 bag, how many were in coach? 0.375. Okay, and I need to bust out the calculator to do this. 0.833, repeating forever and ever. If I'm gonna change this to be a percent, I'm gonna take the decimal, and it doesn't matter that it repeats. I'm gonna take it and drag it 2 to the right. $83.3, repeating. Okay. And then our last one, checked 2 bags, given that they are in first class. How many first class people, how many Richies do you have on the plane? 0.1875. And of the rich people, oh, they had 2 bags. They lived a good life. They're first class and 2 bags. Of these first class peeps, 0.1. Okay, calculator, help me. 0.53 repeating. So I got 0.533 repeating. To change that, drag that decimal 2 to the right. And I get 53.3%. Repeat. Okay. So takes a little bit of time. It takes some time, but it gives you your answer right away. Hey, that's it.